So to clarify this sentence, where I say that the polarization state is a description of the geometrical figure, etc. Okay. Let us take the zeta equals to 0 plane as a reference. As I said, there is no difference. You can take any other very important plane, the situation doesn't change. So if we are in zeta equals to 0 plane, we can rewrite those equations like this. Since zeta equals 0, you can simplify this equation, and this one it will be okay. What do we need to describe the geometrical figure? We need to know two things. First, what is the length of this vector? That is absolute value of the vector as a function of time. And we need to know the orientation of the vector. That is, we need to know the angle, I call it c as a function of time, the angle that this vector forms with the x-axis as a function of time. If I have those two information, I can describe this geometrical figure. So let's take one first important case, that is absolute phase equal to 0 or 180 degrees of phase. That's what it means. And arbitrary values of the EX. So let's start calculating this angle. This angle is clearly the arctangent of this component divided the x component. A simple trigonometrical equation. Now, this quantity is sorry. And this is an angle. As you see, there is no dependency in time. Does not depends on time. That is, the orientation in space of the total electric field is constant. But what about the amplitude? Okay, let's calculate it's a little bit easier, instead of calculating the absolute value, to calculate the square of the absolute value. This is the square of the two components. So it is since those are perpendicular to each other, we have to sum them up like this. So you can collect the cos squared let me omit every time 0, 0, but you know that it is. So what we see here is that the direction is constant in time, but the amplitude of the total electric field depends on time. In particular, goes from 0 to a maximum value. Actually, we have calculated the square value. If we calculate if we take into account also the sign, so we'll discover that the total electric field oscillates along this line. So what is the geometrical figure that the electric field describes on that plane? Nothing. The direction is constant and the amplitude oscillates. What is this? Line. This is the so-called linear polarization. And what happens if the phase is P? Nothing special. If the initial phase, instead of being 0, is 180 degrees of P, there is just a minus sign here. It means that instead of oscillating along this line, the electric field oscillates along this line. Always a linear polarization, but instead of being in the first and third quadrant, will be in second and fourth quadrant. So there is nothing fascinating. Linear polarization is important because a lot of applications, that is a lot of antennas, use linear polarization. Not all of them, most of them. Questions before I wipe up? Now, let me discuss a second very important case. one in which the phase is plus or minus 90 degrees, and the two amplitudes are the same. Okay, what polarization we will find out? We will find. Oh, let me know that. Let me tell you that this term here means simply that in time this is important to with this, but we'll go back to this in a moment. Okay, the equations are the same. What changes is the result. Okay, this is epsilon, but those are equal. But let me write them. Now, plus or minus. I'm considering both of situations. And we have here now those two are equal by hypothesis, so they cancel out. And what we find here, if you remember that the cosinus of omega t plus or minus 90 degrees is minus sinus. This is minus sinus divided by cosinus is tangent. And the arcotangent of tangent the omega t is clearly so it's minus, depends on the sign, so minus plus, minus plus. For the two cases, plus or minus is minus plus. So in this example, the direction of the electric field depends on time. And in particular, the electric field rotates with an angular velocity omega. It makes a full circle in one period. And what about the amplitude? Okay, let's work it out. And we have already seen that this thing here is equal to and this thing here is equal by definition. Okay, this is an X.
¿Por qué se me cuadra?
So we can collect in this equation zero, zero, and then we have and this is equal to 1. This time, the amplitude does not depend on time. It's constant. So the absolute value of the electric field is constant, but its direction rotates in time. What is the geometrical figure?
Circle.
Can be described? A circle. Circular polarization. The sense of rotation depends on sign. We will see this in a moment. If you are looking at the electromagnetic wave that is coming towards you, when the phase is minus p, you see it rotating counterclockwise. And we usually call those the circular polarization. We used to divide this in left-handed and right-handed circular polarization, depending if the electric field rotates toward the left or toward the right. So this is going to be left or right circular polarization, question mark. Yes.
Radio frequency antennas, mobile phone, which is the relation between polarization, electric field,
Polarization?
and electric field.
We were talking about base stations or mobile. We're talking about base stations. The electric field is the field that we give to the antenna usually to illuminate a certain portion of the ground. And this is the direction of propagation.
But it's
Can be mechanical or can be electric.
electric field.
No, you can to do an electric field on antennas. You need more than one antenna. You need an array. Maybe we can talk about this. It's not really focused on this course. But if you have multiple antennas, you can generate by changing the phase between the elements of the array. You can tilt the radiation pattern. But this is it's got nothing to do in principle with the polarization signal. We're talking here of a single antenna or a limit at the limit of a 2 elements. So we're not talking about phase and radio. Okay. So left or right? You have 50% of possible probability to get it right. So this is the probability. Left or right? It depends on which way you look at it. This is the ambiguity. Now, when you say left or right-handed, you always have to be to see things from the point of view of the electromagnetic wave. So you have, in this case, you have to look, you have to imagine to be the electric field of the electromagnetic wave and look into the direction of propagation. In this case, I am rotating like this, so I am rotating towards my right. So this is right-handed circle of polarization. Obviously, if you look at it like this, you will see it rotating towards the left. This towards my left hand. So, that's the last one. Clockwise in this case, and this is left hand. Okay, those are the very typical polarization states. We will usually encounter this kind of propagation or polarization state. It is not. Those are very specific cases, because in generic case, when you have P0 arbitrary and also values of the amplitude arbitrary, the polarization state is elliptical, but is, well, way too complex and is useless to now to derive the ellipse. But in general, what you find out is something like that. The geometrical figure is an ellipse. So the most generic situation is elliptical polarization. Okay, we will then go back to polarization when we need so. For the moment, that's enough as far as the preliminary concepts are concerned. Questions before we move to the proper topics? We talk about bands. Yes, please.
Can you repeat the right-handed and the left-handed?
Yes. Right-handed and left-handed means it's rotating towards my right-hand direction or left-hand direction. But it depends on your point of view. So the definition of right-handed and left-handed polarization start from the assume that you take the wave point of view, not the observer point of view. So you are the electromagnetic wave, you are the electric field of the electromagnetic wave, propagating in this direction, and in this case I'm rotating here towards my right hand, from my left hand to my right hand. So this is right-handed. Other questions? Yes, please.
Device, a microwave device.
A microwave device? Or microwave link? Yes. Microwave link, it depends. Usually for terrestrial link, you take horizontal vertical polarization. Because for a simple reason. First, it is very simple to generate vertical horizontal polarization. And then, if you think about the effects of rain along the link, the raindrops are not spherical. If you look at a raindrop, the real shape of a raindrop is not like you can see on comics. The real shape of a raindrop is like this. While falling into stagnant air. And if you use horizontal and vertical polarization, this shape has no impact, does not change your polarization state. And since you use horizontal and vertical polarization to carry two independent fluxes of information, that is, you make frequency reuse. This choice for the polarization does not mix up the two electromagnetic fields. For different applications, the polarization is different. The choice of the polarization that you make depends on the environment and the kind of application that you want to use. So, since you ask for a point-to-point microwave link, is usually horizontal vertical. Best choice for that particular environment. Okay. Say it again. Galapagos. From mainland to Galapagos, I think it's not possible to, well, it's 1,000 kilometers, isn't it? From 2,000. Yeah. So a direct connection is quite difficult. You want to use a satellite. Island to island. I think it really depends on the environment, but usually for point-to-point situation, horizontal vertical is usually the best choice. Yes. Okay. If you have reflection from, if you are on a line of sight and you have a reflection from the water, then usually you can choose vertical polarization. Because the surface of the water, but we will discuss this when we talk about reflection from the ground, is the same thing. The reflection coefficients are different from horizontal and vertical polarization. So they are very different. So usually you choose vertical, but this is the case where you have a strong reflecting surface. You have two contributions that we will talk about this. From when we talk about reflection from ground or water or whatever. Okay, more questions? Okay, before we move on, let me just show you. Someone can turn on the projector. With the remote control. Okay. Will eventually become. Okay, so what you see here, or you should see here, is this is a plain linearly polarized electromagnetic wave. This is an animation where you see in red is the electric field, and in blue is the magnetic field. They are perpendicular to each other. The energy is going into this direction, into the, in this case, y direction. And you can see those are the vectors in a given point in time. You see the electric field and the magnetic field. They are perfectly in sync. That is, when one is 0, the other one is 0. When one is maximum, the other one is maximum. And the distance between the two maxima is what we call the wavelength. This is the electric field of a circularly polarized wave. So those are the two components, x and y. They are out of phase of 90 degrees. And this is the resulting electromagnetic wave. The field of the resulting electromagnetic wave. What is not shown on this picture is the magnetic field. The magnetic field is always perpendicular at the electric field and will be rotating at the same speed. So if you try to draw on this picture also the magnetic field, you end up with a big mess with spirals one into another. So you have to imagine the magnetic field as a vector that rotates, stays perpendicular in space to the magnetic, to the electric. Okay? This wave is propagating in the negative z direction. This is a left-handed polarization. So the right-handed polarization will be rotating on the opposite side, but will always be propagating in the negative z direction. So this is I hope this helps. Okay. Okay. Bands. Let's talk about bands and propagation models. Okay. I will discuss the general properties of the bands, and then we will actually focus on a subset of the bands that we talked about. Okay. Now let's start with very low frequencies. The first band that we find is going from 3 kilohertz to 30 kilohertz. Very, very low frequencies. The wavelength wave lambda is incredibly big. from 100 to 10 kilometers. Those are the so-called very, very low frequencies, VRF, very low frequencies. Users, applications of those wavelengths, mainly military. In particular, since the lower the frequency, the deeper the penetration of the electromagnetic wave in lossy media like water or ground or salt water, seawater. Those very low frequencies can penetrate the surface of the sea for several meters. You can imagine what they're used for. To communicate with submarines, military submarines. At very low speed, because you have a very, very narrow bandwidth. So you cannot, your bit rate must be very low. But good enough to send some other signals. What is the trouble with those low frequencies? We will see that for an antenna to be effective, it is important its size. The size of an antenna is important. Not the size in absolute, but the size with respect to the wavelength. So the size must be a significant fraction of the wavelength. Let's say a quarter of the wavelength. So you can imagine building up an antenna that is 2 kilometers in size. It's not extremely easy. Those frequency bands, as far as we are concerned, are of very practical use. So we will not consider them. The next band is that goes from 30 kilohertz to 300 kilohertz, so we go from 10 kilometers to 1 kilometer. And this is called low frequencies. On those bands there are some applications. There is some broadcasting, mainly in Europe and Africa. I think that is not permitted in this part of the planet. So you will not find broadcasting here. And obviously military. The particular, okay, I will discuss this in a moment. Maybe together with, no, I will discuss it now. Propagation mode. Each electromagnetic wave propagates in a different way. So, propagation mode for those two bands is the so-called ground wave. in particular the surface wave. I'll tell you in a minute what it is, the surface wave. When you, let's imagine that this is the Earth. When you solve the Maxwell equation, we have said that the plane wave is a solution of the Maxwell equation. It is not the only possible solution. There is another solution that is called surface wave, and it is an electromagnetic wave that does not propagate along the straight line. It is an electromagnetic wave that propagates along the surface of the Earth. It's actually following the curvature of the Earth. So if you have a transmitter here, the surface wave actually travels following the Earth's curvature. Obviously, impacting waves when it propagates. But nevertheless, at those frequency bands, it's not unfrequent to have a coverage of up to several thousand kilometers using the surface. Those are the dominant propagation modes. Again, for our application, for mobile and wireless propagation, for mobile and wireless communication system, the antennas would be still too big for portable mobile devices. So we are not interested in that frequency band for our application. The next frequency band is the so-called medium frequencies. 300 kilohertz to 3 megahertz, wavelength 1000 to 100 meters. Okay, the main application, there are a lot of users here. The main application that you will possibly know is broadcasting. I think you call it onda larga, onda media, medium waves on your domestic receiver. La M, modulation de amplitude modulation, broadcasting. Utilities. Now this band is interesting because during the day the main propagation mode is again ground wave. Surface wave. But the attenuation is stronger. The attenuation of the surface wave increases with increasing frequency. So this frequency band, at this frequency band, the ground wave is more attenuated than at lower frequency. So the distance is smaller. So with the ground wave at those frequencies, you can cover up to a few hundred kilometers, not thousands, few hundred kilometers. During the night, you have the so-called ionospheric or sky wave. Now, what is this? If you look at the atmosphere of our planet, at a height of about between 100 and 400 kilometers, so we are talking about of height that are well above the flight height, for example. So we're talking 100 to 400 kilometers above the ground. There is a layer that is called ionosphere. This layer is generated by the radiation of the sun. So in particular, the ultraviolets, the hard ultraviolets and the X-rays generated from the sun ionize this layer. It means that, in a sense, it's a kind of conductive layer. There are free electrons that are able to move. So for those frequencies, under particular conditions, the signal can bounce back from the ionosphere to the Earth. So the name sky wave, because if you are the receiver, the signal apparently comes from the sky. It's coming from your sky, but it's not really actually coming from the sky. It's bounced back over the ionosphere. Now, during the night, during the day, this is, I will not go into the details, but this wave is highly attenuated, so during the day it does not exist. And it appears all over magic during the night. You can do an experiment yourself if you have, surely you have at home one of those AM, FM portable radios. If you switch to AM and you do a scan of the medium wave band during the day, you will just hear your local stations. If you do the same test during the night, you will possibly hear stations coming in from all over South America or Central America. That's because during the night you start getting the ionospheric signal. Regrettably, even if the distance that you can cover is very large, we are talking hundreds or thousands of kilometers during the night, still the dimension of the antennas would be unmanageable. So we have to move up in frequency. HF. The next band from 3 MHz to 20 MHz, wavelength from 100 meters to 10 meters, is called HF, high frequencies. You will find a lot of users fighting for this frequency band, in particular military and utilities. Because the dominant propagation mode is ionosphere. It means that depending on the condition, you can find frequencies that can bounce back. Actually, they can make multiple bounces, and you can have a global coverage. You can actually communicate with any point on the planet with a proper choice of frequency and time. This is the way the communication system, the early communication, long distance communication systems worked before the advent of satellite. But even today, those frequency bands are of interest. There are a lot of silent users on those bands, mainly military and civil protection, because it's the only frequency band that has global coverage without infrastructure. You don't need an infrastructure, you don't need a satellite, and in case of crisis, war, natural disaster, whatever wipes out your communication infrastructure, that's the only way you can, the only frequency band you can use and have global coverage without infrastructure. Now we say, okay, but we have satellites, but those are infrastructures. If something wrong, if something horrible happens, that's the only way, the only frequency band where you can communicate beyond the horizon. Okay, that's why there are a lot of users that are there silent because military use satellite, but if something is wrong, they are ready to use this frequency. Okay, still unmanageable antennas. And then there is not too much people there. So we move up. And we eventually go to our first band of interest.